Welcome you to on this another video lecture in the series of discrete mathematics, which is of MCS 212. So in this lecture I am going to discuss about the principle of mathematical induction, right? And there are one or two questions that are asked in your exams uh, every time. So, what is the principle of mathematical induction and what this principle says? So, I will first I will tell you the theorem, and then I will take two examples to prove uh, some equation using this principle, right? Okay, so a principle of mathematical induction says that to prove that Pn is what? P is your proposition statement or function, right? So to prove that this P function is true for all positive integers, for all positive integers n, okay, where Pn is a where Pn is a propri where Pn is a propositional propositional function propositional function, right? Okay, now so to prove that it completes in two steps. Okay, it completes in two steps. And what are these steps? These steps is, first step is your step basis step, or you can also say that this is the very first basic step. Okay, so in this step we verify that P1 is true. P1 is true, right? And the second step, this is the first basis step. The second step is inductive step. Okay, inductive step. So inductive step is your that the conditional statement the conditional statement I am writing in short STMT for statement that PK is true, and it implies that PK plus 1 is also true, right? Is true for all positive integers, right? Positive integers. So this is the definition, because as I have seen in some papers, previous year papers of discrete mathematics and BC and MCA, that they ask about the definition of or principle of mathematical induction. So sometimes they ask the question that state the principle of mathematical induction. And what do you mean by principle of mathematical induction? So for that you have to write this definition. I just write and with these two steps, right? So let's take an example that how this principle works and how we can prove that is some given propositional function which is Pn is true, right? So a question is asked in your exam that if n is a positive integer, if n is a positive integer, so prove that this 1 plus 2 plus n is your n plus 1 by 2, right? Okay, so to prove this, what we have to do, the proof is, as we know from our theorem, that we have to prove it for p1 and then for pk and then for pk plus 1 as well, right? So first is your let pn be a propositional function, right? Prepositional function, and prepositional function, right? Then for basis step, which is our first step, which is basis step, and in this step we have to prove it for p1, right? So for n is equal to 1, so here n is equal to 1, so this series up to n, so the LHS will be your 1, right? 1, and then RHS will be your, put n equal to 1 here, so it will be 1 into 1 plus 1 by 2, and it will be your 1 into 2 by 2, so 1 into 2 by 2, which is a 1, right? So that means this equation or this function is true for p1, so we can say that p1 is true, right? And then the next step is your inductive step. This is your last step, so inductive step. So for this we have to prove it for k, okay? So if pk holds for a positive integer k, then we assume that if pk holds true, then we write this as 1 plus 2 plus till k, right? Because we are proving for n is equal to k now, so it will be k plus 1 by 2, right? And then under this assumption, okay, under this assumption, we have to prove for n is equal to k plus 1, because as we know from the definition, so let me write this as this pk holds true, then it implies that it will be hold true for the next number, which is p of k plus 1, right? Okay, now what we have to do, we have to add k plus 1, because this is up to k, and then we have to prove it that it is true for k plus 1 also. So it will be, we will write this as 1 plus 2 plus this and so on plus k, and then for the next number, which is k plus 1, obviously, right? For k plus 1, right? So put k plus 1 here, right? In place of k plus 1 in this equation, right? K, and then it will be k plus 1 plus 1, so it will be k plus 2 by 2, right? So this is your equation. Now if you look this equation, which is let me write this for equation 1. So if you put this value, because 1 plus 2 up to k terms is k plus 1 by 2, so here we have to put this value, right? So this is k plus 1 by 2 plus k plus 1, right, is your this one, right? So if this LHS is equal to RHS, it is your RHS, then it will be true for k plus 1 as well, Okay, so so just calculate this side, right? So it will be like, if you put 2 here and then take LCM, then this will be your k plus 1, right, plus 2k, right, plus 1. Okay, now solve for another steps. So it will be like k into k, which is k square plus k plus 2k plus 2, right, by 2. So it will be uh, k square plus 3k, right, k square plus 3k plus, right. So now, okay, now you have we have to prove for this, right? So k, if I take common k plus y2, and then this is 2k plus 2, right? So is it will be k square plus 3k plus 2, right, by 2. And then if you solve this equation, it will be like uh, k plus 1 into k plus 2 by 2, right. So it will be your equal to RHS. Now we can say that the LHS is equal to RHS. So it's hold true for, so P plus K1 is true, right. So like that you can take another examples to solve these type of questions, right. I hope that uh, it will help you to understand this concept. So let me take another example, right. The other examples that I will take is your that these questions have been asked in your exam, previous year exam. So I'm taking these examples from there, right. So this is another question. So that 1 plus 2 plus 2 square plus up to 2 raised to power n is equal to 2 raised to power n plus 1 minus 1, right, for all non-negative integers n. Okay, so the basis step, right, so the basis step will be your because it is saying that it is for all non-negative integers n. So here in the basis step we will because it's for non-negative integers, so we will put the value n as 0, right, for n is equal to 0. So in this it will be 2, in LHS it will be 2 raised to power 0, which is n, and in RHS it will be your like 2, 0 plus 1 minus 1, which is again 2 minus 1 and 1. So here we can see that RHS is RHS, so it holds true for n 0. So that means P0 is, right, that means P0 is true. So when P0 is true, so in the inductive step we have to prove it for K, right, we have to prove it for K, right. So it will be your n is equal to K. So put n is equal to K. So this equation will be 1 plus 2 square plus till 2 raised to power K, because n is now K, and then will be 2 raised to power K plus 1 minus 1, right. Okay. Now when we have proved that assume that n is equal to K, and which is true for Pk. If it is true for Pk, then it holds that it will be true for K plus 1. So again putting n is equal to K plus 1, we have to prove this induction. So 1 plus 2 square plus, okay, so on until 2 raised to power K and then add 2 raised to power k plus 1. So for the next iteration, which will be 2 raised to power k plus 1. So don't confuse with this, because in the last example we have seen that we have put k plus 1 only, but here because this is the series of 2, so we will add k plus 1 term as 2 raised to power of k plus 1. Okay. Now put k plus 1 here. Okay, so it will be k plus 1 plus 1, so it will be 2 minus 1. So again, if I write this equation as 1, and then you can replace this with this, so it will be 2 raised to power k plus 1 minus 1 plus 2 raised to k plus 1, right? So this is your LHS, right? So we have to prove this LHS is equal to RHS. It is your RHS. Okay. So here we have k plus 1, and then we have k plus 1 or minus 1. Okay. So now we can write it as 2 k plus 1 minus 1 plus 2 raised to power k plus 1, right? Okay, and we can write it as 2 into 2 k plus 1, right, minus 1, right, and then it is 2 raised to power 1. Okay, so it will be the powers will be added, right? Powers will be added, so it will be k plus 2 minus 1. So it holds true for p plus p, k plus 1 holds true for all non-negative integers. So non-negative integers. So in non-negative integers, 0 will come, right? So 0 will the first case. So that's why I have taken the p0, right? So in that case, we can prove that this is your proof by mathematical principle of mathematical induction. So you can try some of the questions as your own, and if you have any doubt and questions, you can ask me, right? So thanks for watching, and your suggestions are always welcome. Thank you very much.